Hi everyone. As I said in my previous video, I'd like to make more videos for my blog because I think it's a nice way to demonstrate and explain different statistics and really dig into the analysis. This is video 2 and also the promised 4th post in my series on meta-analysis in R. In my previous 3 posts, I discussed the different components that go into a meta-analysis. First of all, the individual study effect sizes, which are each trying to estimate an underlying population value. The variance associated with these individual effect sizes, which is based on study sample size, so that larger studies have smaller variance and smaller studies have larger variance. This is because we assume that larger studies have more precision and are better able to estimate that population value. And lastly, the weight given to each study, which is often the inverse of variance. There might be some other ways to calculate weight depending on what exact effect size you're using. I won't go into that today, but I plan on writing some future posts on those topics, so stay tuned. These weights are used when you're conducting the actual meta-analysis because meta-analysis is a weighted analysis so that the average effect size is more strongly determined by studies that have smaller variance or larger sample size. I'll be sure to provide links to these previous posts in the video description, and I'm also reusing code that I introduced in those posts. So I have 2 data sets that I've been working with. The first one uses standardized mean difference as the effect size, and the other one uses log odds ratio. The effect size metric should be determined by the type of data that the study collected, and you should never combine these values into a single meta-analysis unless you convert all values to being on the same metric. There are ways to do that. Again, that's another post for another day. Today, I'm just going to be working with the SMD meta data frame, the standardized mean difference. So I'll go ahead and run that. And we're using the metafor package for everything today. There are other R packages that can be used to conduct meta-analysis, but for our needs today, metafor can do everything. So I'll go ahead and load that library and also have it calculate those effect sizes for me. In the W post, I performed a fixed effects meta-analysis. So I'm going to rerun that and generate my output. We can use information in this output to help us inform whether a random effects analysis is more justified. And in fact, a random effects analysis is usually more justified than a fixed effects model. Why is that? So a fixed effects model assumes that there is only one true population value. If we could look into a crystal ball and see what the actual effect is without measurement error and sampling error, threats to validity, everything that can introduce noise into your study and analysis. For a bunch of studies that use the same measure or similar measures and similar populations, that might be true. There might only be one true population value we're trying to estimate. A random effects model, on the other hand, assumes there is actually a range of true population values, which might depend on different factors. Some that we can measure, like differences in how the study was conducted or differences in study population, and some that we can't measure. These factors introduce variance into our study effect sizes. Some of that variance is sampling error, and a fixed effects model assumes that the only source of variance is sampling error. But some of that variance might be systematic. There's a hybrid approach you can use called a mixed effects model. That usually requires more complex analysis than what I'm using today. I actually used mixed effects for my own meta-analysis. I personally think it's the best approach. Random effects is probably the second best approach. Fixed effects is last. But again, it depends on what data you're working with and what you plan to do with it. So look for a future post on mixed effects analysis. So before I go into a random effects analysis, let's take a look at the fixed effects output. At the top, we see that it states that a fixed effects model was used. This is good to confirm that you ran the right code. We also have K equals 11. K is the number of studies in the meta-analysis. Once again, we should confirm that that is correct. If we look at our data set, we see we have 11 observations. And if I went through this original data frame creation code and counted, I'd probably want to confirm that there are in fact 11 studies. This is a good thing to check just to make sure that your data is correct, that your model ran properly, and that there aren't any problems. So we have the values I talked about before. We have our model estimate, which is the mean effect size and the standard error associated with that estimate. Because our studies have sampling error, we assume that our mean effect size isn't the exact estimate of the population value. It's an estimate within a margin of error. That standard error is used to give us a 95% confidence interval, which is our margin of error around that overall mean effect size, that estimate. We also have a z-test and p-value, which tests whether our estimate is significantly greater than 0, and we see that it is. But here's a value I didn't talk about before, the test for heterogeneity. This value tells us whether we have significantly more variance in our effect sizes than we would expect by sampling error alone. So the Q statistic is actually based on the chi-square statistic, and it's significant, meaning we have significant heterogeneity, more than we can explain by sampling error. This means a fixed effects model is not justified for these data, and we need to use either a mixed or random effects model. Now, in a random effects model, you have two variance terms. The standard error, that's associated with the mean effect size, that's the sampling error, and a random effects variance component, which is called tau squared. Metafor gives multiple random effects estimation methods, and you'll notice I already have the RMA function pulled up over here so we can take a look at what those different methods are. There are many methods listed here. We'll scroll down to specifying the model. There are many listed. You really only need to concern yourself with two of them. The Dear-Simonian-Laird estimator, or DL, and restricted maximum likelihood, or REML. Now, DL is based on the Q statistic, that measure of heterogeneity, and it uses methods of moments estimation. Method of moments is a Pearsonian concept referring to Carl Pearson. REML uses maximum likelihood estimation, which is an iterative technique. Maximum likelihood, although not created by him, was popularized by Ronald Fisher. The fact that these are the two most recommended methods is funny to me because Pearson and Fisher had a bitter rivalry. These guys hated each other, not only because they were both brilliant and annoyed by anything they perceived as lack of brilliance, but also because they were super petty. Pearson blocked some of Fisher's publications and blackballed him among many statisticians out of sheer pettiness. But then Fisher was kind of a condescending know-it-all who was easily hurt when people disagreed with him, so he didn't really help his case. Personally, my favorite Pearson is Egon, Carl's son, who made some really important contributions to the field, but is underrated because he's overshadowed by his father, Carl. But then I always root for the underdog. In simulation studies, REML actually appears to give more accurate estimates, so I guess score 1 for Fisher. In my experience, the values these two methods produce don't really differ much, so pick your favorite. Or if you're responding to a revise and resubmit and you really want your paper to be accepted this time, use reviewer 2's favorite on pretty much everything. So let's run our random effects model on this data set. Just for fun, we'll use both DL and REML. And you'll see I've already written that code here. So I'll go ahead and run those two models, and then we'll take a look at the output, and you'll see that they don't really differ too much. So let's look at our summary. Once again, we see at the top the kind of model, in this case random effects model. K is still equal to 11, this is good. And we see that the tau square is estimated using DL. If you scroll through the output, we see a few new things. So here's our tau squared, the random effects variance component. One thing I'll point out is it's not a big deal to run both fixed and random effects model. First of all, your fixed effects output will tell you if a random effects model is better suited with that Q statistic. And if a random effects model is unsuited, but you went ahead and ran it anyway, your tau squared will be 0 or very close to it. We also have a few more things under tau squared. So we have I squared, which estimates the percentage of heterogeneity that is not attributable to sampling error. Almost 90% of the variance cannot be attributed to sampling error. That's a strong justification for a random effects model. We also have H squared, which is a ratio of total variability to sampling variability. If the heterogeneity can be explained by sampling error alone, this value would be 1, or very close to it. It's almost 10. Again, there's a lot of heterogeneity in these data. So all of this together provides justification for using a random effects model. You'll notice that our estimate is larger. Sometimes this happens with a random effects model, but not always. The value might be smaller, it might be the same as a fixed effects model. This is because the random effects model adds the tau squared onto the study variance, which impacts the study weight. So this is an average based on different weights than we used for the fixed effects model. Our standard error is also larger for the same reason. Our random effects variance term has been added. And our confidence interval is wider. More variance, less precision, wider confidence interval. So what happens if we look at the REML output? So once again, confirming at the top, tau squared estimator used as REML. Our estimate is 0.5209 compared to 0.5232. They're pretty close. They're different, but they're close. Our tau squared is different, not by a lot. Our standard error, 0.1754 versus 0.1702, and our confidence intervals are pretty close. So the results are different, but they're very, very similar to each other. For a smaller meta-analysis like this, the exact estimator that you use is really a matter of preference. Now, your tau squared is not only used to correct those study variances and the overall standard error and the weights that are used, it's also used to give us a prediction interval. Now, the confidence interval is the margin of error around the mean effect size. But a random effects model does not assume that there is one true effect size. It does not assume that this mean represents all studies on this topic. It assumes that there's actually a range of true effect sizes. Tau squared is used to generate that range, which we call a prediction interval. The true effect sizes can fall between those values depending on those factors that are unmeasured but systematic. If a mean effect size is significantly greater than 0, the confidence interval will not include 0, or it shouldn't include 0. But a prediction interval absolutely can include 0, and it often does. It's because these intervals are telling you two different things. When I tried to publish my meta-analysis, the reviewer one of the reviewers absolutely did not understand the distinction and refused to accept the explanation. But I just read a great article a couple of days ago in the British Medical Journal Open that is literally called Plea for Routinely Presenting Prediction Intervals in Meta-Analysis. In fact, I have that article pulled up here. This is open access, so I'll be sure to share the link in the description for this video. Cite this thing in your meta-analysis reports. Seriously, stick it to reviewer 2. Rant over. So let's compute our prediction interval. We'll just use the REML results for this example. So the prediction interval requires a few pieces of information. First of all, what kind of prediction interval you want to compute. 95% is most common, but you could use other values like 90%, which would give you a narrower prediction interval, or 99%, which would give you a wider interval. The equation for prediction interval uses a t-value, and that t is based on your alpha. So for a 95% prediction interval, your alpha is 0.05 divided by 2, since it's a two-tailed test, as well as your degrees of freedom, which in this case is k minus 1. You also need your pooled standard deviation. And for a random effects model, you have two sources of variance. You have your standard error, and you also have your tau squared. The equation recommended in the BMJ article is to square the standard error, add the tau squared, and then take the square root of that. And finally, you need your mean effect size, which in the meta-analysis results is abbreviated as B. So I need to calculate a few things here. First of all, I need to use this prediction interval to get my alpha. I need to get my t critical value, and the R function for a t critical value is qt, so we'll base that on alpha, as well as k minus 1. Now we can get that k value directly from our output, which I'm just going to abbreviate as x for now. And I want to make sure that it doesn't give me a negative value for that t, so I'm going to have it give me the absolute value. Once again, I'm going to abbreviate the results. The Remmel results is x. And so I can use those pieces of information to give me the low side of the prediction interval and the high side. So the low side is just the effect size, the mean effect size, minus the product of the pooled standard deviation and t. The high side is exactly the same except it's additive. And last, because I want to make this really easy on myself, I'm going to have R paste the results for me, including a little indicator that tells me what prediction interval I requested. And to keep it from giving me lots of decimal places with those prediction intervals, I'm also going to have R round things off to 2 digits. So I just wrote a bunch of code that I want R to run for me with the output and the prediction interval I specify. So I'm going to enclose this information in brackets and make it a custom function that I can just reuse anytime I want a prediction interval. And I only need to give it 2 pieces of information, x, the name of the output results, and pi, the prediction interval that I want. So let me just quickly scan over this and make sure that I didn't make any mistakes. Everything looks fine. So we'll run that code, and then we'll produce our prediction interval for our Remmel results. We'll do a 95% prediction interval. There we go. So the low side is negative 0.69 and the high side is 1.73. Just like I said before, a prediction interval absolutely can include 0 and negative values. What this means is that studies on this topic of the meta-analysis can find the opposite effect of that mean effect size, and the opposite effect of most of the other studies. That's not unusual, and it could be determined by a variety of factors, like what kinds of study stimuli were used, or the particular population that they might have reacted to the stimuli different. So there's a variety of logical explanations of why a study on a topic may find a result that is opposite of what most of the other research on the topic finds. And it doesn't necessarily mean that the results are wrong. All right, last up, generating visualizations of meta-analysis results. So metafor gives you a couple of options, forest plots and funnel plots. Forest plots are used to display the individual study effect sizes and confidence intervals, as well as the mean effect size and confidence interval. By default, metafor labels your studies 1 through k. And here, I'll show you what that looks like. Well, what if I want to use custom labels? What if I want this to say the name of the study author and the year that the study was published? You actually add that information when you run the meta-analysis itself. And then that information is used when you're producing visuals. So you just add the argument slab, which I'm sure is just short for study label. And I'm going to have it include two pieces of information. So author and year is a variable in my data set, which includes the name of the first author and the year that the study was published or that it was presented, or for unpublished studies, the year it was written according to the author. And then also study number, because different articles contributed sometimes multiple studies. So we'll just rerun that, and then we'll rerun our forest plot. And you'll see now I have name of the first author, the year of publication, and the particular study that is included in the meta-analysis. So Ruva 2007 had 2 studies. Krzyzanowski 2006, only study 3 was eligible for this meta-analysis, and so on. Funnel plots are used to detect publication bias. So the assumption is that smaller studies should have more variation around the mean effect size, while larger studies should be closer to the mean. So you can draw a funnel from that mean effect sizes. Smaller studies should fall at the wider part of the funnel, and larger studies should fall at the narrower part. If values fall outside of the funnel, this is believed to be evidence of publication bias, that the articles that are being published are not following this pattern. This issue is hotly debated, and funnel plots are somewhat controversial. I'm not a big fan of them. They're really not my go-to visualization, especially because if you're doing a meta-analysis properly, you're not only including published studies, you're reaching out to big names in the field that you're doing the meta-analysis on, you're doing an exhaustive literature search and searching not just for publications, but presentations and unpublished papers, things that people have in their file drawer. So if you're doing that properly, the funnel plot is kind of meaningless. Obviously, you can't find everything. Anyway, so here you can see standard error of 0. So this is where the larger studies would be, and where the mean effect size is. And then this is where the smaller studies would be that have greater standard error. Most of the effect sizes fall within the funnel. We have a couple over here falling outside of it. Like I said, some people would say that this is evidence of publication bias. Funnel plots aren't my go-to analysis, but some people like them, and sometimes reviewers request them. So if they do request them, as you can see, it's really easy to do with the metafor package. All right, there you have it. Enough about meta-analysis and R to be dangerous. So look for links related to posts in the descriptions, or below this embedded video if you happen to be watching on my blog, and thank you for doing that. And I'll also be including a work example mirroring this process with the OR meta dataset. And if you'd like to test yourself and test your knowledge, you could try running that meta-analysis before examining my code and see how you do. So thanks for watching.